Swamiji. I, Dr. Gayatri HM, would like to welcome you all for second day PDP Professional Development Program and Journey through Semiconductor Industry segment delivered by Vijay Kumar ND. Now I request Chandrasekhar, Professor Chandrasekhar, to welcome him. Now I request Dr. S.D. Rudraswamy sir to introduce today's resource person. Shri Vijay Kumar ND, Director, Professor, Bangalore. Thank you.
Very good morning. Namaskara. Very good. Self-active. Yeah, so it's my pleasure and also honor to introduce this session's speaker, ND Vijay Kumar sir. I want to share one important aspect of ND Vijay Kumar sir. So without his knowledge, I copied one of his teaching skill and I am implementing from day one. So he was my guru in my undergrad program at BIT Davangere. So sir, I think I have told this to you. So he is the person who used to go without any teaching aid to the class. Okay, so he used to just carry the attendance register along with the chalk and duster. Apart from that, nothing. So that inspired me from my undergrad days, and from day one at SJC I am following. So one additional thing is I even don't carry the attendance as well as this, but somehow I take the attendance in my own ways. Okay, so that's about the small thing that I wanted to share. So coming back to his professional experience summary, a senior professional in physical design with 23 plus year of experience in leading MNCs and significant practical experience in designing various unique devices and design flows. So 23 plus years of experience in industry, I think more than 10 years of experience in academic. Okay, so I still believe that he would have been a best academician rather than this, because I heard his teaching that time. So continuing now, he is currently working as a director at Proxelera Bangalore, which is an VLSI company. Previously, he worked as a physical design director at Ernst Semiconductors Bangalore. Worked as principal engineer in Silica India Private Limited Bangalore from 2020 to 22. Before, he worked as a manager at Visit Design Technologies, a senior staff engineer in Intel Bangalore, senior technical leader in Mega Chips Corporations. And I think if I just keep on saying, I think the list goes on. So he has played an important role in all aspects of VLSI design. Sir, without any further delay, I request you to take the dais. Okay, so this is all about the ND Vijay Kumar sir. Thanks.
Thank you, Rudraswamy, for the
nice introduction. I quickly go through one introduction, so we capture all the audience, okay, what is my interest and where actually we stand.
So I think I can use without this mic only.
Okay. So that's why just I would like to give my introduction.
So this one, okay. So totally. So again, I will repeat again. So thank you very much, Rudraswamy, for giving a nice introduction. So so I totally loved my profession. Teaching profession is my ultimate thing, and I used to whatever he said. Okay, so that I followed from one of my senior. So I used to go to class without any, so I used to prepare for 2 hours without, before going to the classroom, and I used to write all the circuit diagram. My pet subject was linear integrated circuit system, and I used to design all micro op amps, okay, MUA 741. And another subject which was interesting for me was antennas, okay, when I was in teaching academic line. And my experience was in academic line from 91 to 2000. And so today's agenda, I will just quickly go through it. So first I will give my biopic, so where you will get, you can get the rhythm, okay. Your audience are there, they are interested in some communication projects, they are interested in some real estate projects. So you will come to know, so what is my experience and what you can expect from me, okay. So in real estate design, real estate has so many domains, okay. That means you have front end, back end. So I am into back end, so where my expertise are into physical design. So I'm completely, if you compare it to civil field, I am like mason, okay, mason worker. And so this is my experience and this is my bread and butter for now. So quickly I'll go with my biodata. So then the introduction to semiconductor. So I'll give you what exactly the semiconductor sound, how it is going on. And whatever the subject which is given to me, so it is like never ending saga, okay. So I cannot constrain these things. So I am mixing these things with the technical things which is happening now in the industry, because you are not aware what exactly the things which are going on in the industry now. So just I will quickly go through what semiconductor industry and what are the things which we need to be capturing, okay. So those things. So also I will touch upon the history of the semiconductor industry. I will give my own gadget, okay, whatever. If you see here the audience, okay, we are all of 1965 to 1990 born, okay. So those kind of things, how was our electronics journey when we were kids, okay. Or when did we see our television, when did we see our first tape recorder, all those things I will give you quickly through the semiconductor application domain, semiconductor fabrication units, what are the fabrication units are, current trends in the semiconductor design, challenges, solutions, and summary and question and. So this is my introduction. So usually when teaching, right, in teaching I used to be called as NDV, okay, NDV Jay Kumar, and highest qualification ME. So and I did my post graduation in the year 93. So that is from Karnataka University SDM CET. So this is, and my past year is 1991 engineering, and it is from Mysore University. I can proudly say that I am from Mysore University. So and VTU was not that there at that. And my alma mater is BIT, Bapuji Institute of Engineering and Technology. So and my very beloved subject or the experience academic line is my so even today also, if I get dias, I can talk to the students, okay, for around 4 hours without anything, without any preparation. So and I was very zeal to continue in that profession. But during the 2000s, so there was a lot of scope for real estate engineers. So I got the opportunity in one of the company. So I joined real estate profession. So academic experience of solid 9 years and served as lecturer in ANC department, BIT Davangere, and industry experience of 24 plus years, and still I am going on, and my experience is still there, and I worked in various capacity from member technical staff, okay, to senior director in product and semiconductor design services company. So I am still hands-on. So with my experience of 24 plus 9, I am still hands-on. I am doing still floor plan. I still do DRC LVS checks and DRC LVS fixes. So that's why I am there intact with the industry. So what I request here is, whenever you come to industry, you should not say that when you become director or CEO, or our CEO must be knowing, Ravi Shankar sir, still he is doing simulation and he is debugging the simulation waveforms where the problems are there. So yesterday night also I have fixed some of the DRC LVS problems and I came to this discussion. So these are the things we need to catch up the what the industry is going on, and we need to be acknowledge those things, and we need to continue our learning, okay, day-to-day learning from these aspects. I am specialist, I can say that proudly, that I am RTL to GDS, so register transfer level to GDS or the YSS implementation in lower technology nodes. So already heard of that, what the technology we are moving into is 1.8 nanometer, okay, 18 angstrom they call it in Intel, and lower technology nodes. And it is, and also I am expert in ASIC methodology, so wherein I can set the flow for RTL to GDS implementation using all the tools, okay, Cadence, Synapsys or Mental Graphics. flow development, on-site deployment, and worldwide support. So next comes to the main topic of today's background or today's main discussion point is semiconductor. So we are so now if we see any of the newspaper or technical journals or any emails, so a lot of tremendous scope is going on with semiconductors, right? So our VLSI design. So what exactly is there? So because whatever we request or whatever the application you need, okay, that needs to be come from the semiconductor, or it needs to be come from the VLSI, because the requirement of the end user, which is not only limited to the current requirement, or we need to catch up with the whatever the request we have from the technical aspects of it, and we need to develop it. So based on that, so this is the introduction slide. Okay, what is semiconductor? I already studied in physics, and nowadays from A standard only, the students are learning this in the science subject. What is they are explaining what is semiconductor, okay, and all. So as the property itself, it says that the materials with electrical conductivity between that of a conductor, like copper and an insulator. The main problem here is, or the main advantage here is, we can control the electricity with controlling those conditions. So these are the key properties. Conductivity can be controlled by adding impurities. So you are all professors, you can give hours together lectures on the semiconductor, okay, and temperature sensitivity and the band gap, if you say this one. So semiconductor, so to understand the device physics and to understand this one, you need to be master in the physics. So there are a lot of things which are going on in this. And again, the importance, why we are giving such an importance to semiconductor devices or semiconductor transistors. So because foundation in modern electronics, used in bipolar, field transistor, versatility, enable the creation of small, efficient, and powerful electronics. So these are the application you are not. So any tool or any gadget you take, so these are all the things you are using it currently now. So this is my introduction slide. So next I will also, if you see the topic which is assigned to me, so I need to give the introduction of history, because whatever the Pitamahas are there, right, founders, it is our, in this platform, it is our responsibility, okay, to remember them, okay, and give one big salute to them. So the first it was developed, okay, 1900, okay, discovery of the semiconductor properties. So it is on very basic level. So they explored on the silicon and germanium, how the qualities can be, the semiconductor qualities can be imbibed into those material, and how we can control the electricity, okay, the electrons movement and all was covered in 1900. Okay, and 1947, say the gap of 47 years, which was invested, okay, on the invention of the transistor by Pitamaha John Bardeen, okay, and Walter Britton and William Shockley. There is Shockley diode itself is there in his name, right? So these are the things, because you see the semiconductor to 47 years they took to explore or to find out the semiconductor properties and to introduce the transistor, okay, whatever NPN, PNP transistors we have, right? So that is the done by Bell Labs, marking the birth of modern electronics. So whatever we are there, VLSI, whatever the devices we are using, whatever the gadgets we are using, we should, so it is our part and parcel of our responsibility to commemorate them and to appreciate their work in their duration. Okay, then key milestones. What are the key milestones we achieved? So 1950s, development of first silicon transistors and establishment of companies like Texas Instruments, okay, and Fairchild Semiconductors. So that is Fairchild, which converted into HP, right? So Fairchild, if you see, still if you see our some of the ICs, okay, New 741, you can see it was printed on that Fairchild, right? So these are the companies, founder members. So nowadays there are a lot of companies are there. Qualcomm, they are Intel, and they are making money like anything. But so these are the companies, okay, which started the electronics. Okay, they started electronics, and all the companies who are later started, right? They were all worked. I am proud to say that I was also associated with Texas Instruments in 2003 to 2004. As a contractor, I worked on a chip called it is a Megastar. Okay, it was a DSP processor. I worked in Texas Instruments. It was on 65 nanometer design. That was in 2003 to 2004 timeline. So then 1960. So we know that we have the concept called small scale integration SSI, 7400 gate, 7410, 7409. Okay, so all those gates, there are small scale integrated chips or integrated circuit chips, right? So dual inline package. So that is in 1960, the integrated circuit designed by Jig Kilby and Robert Nice, revolutionizing electronics by combining multiple transistors on a single chip. So that is what the integrated circuit. The circuits are integrated, are connected properly to perform the predefined function. If you have NAND gate, okay, 7400 NAND gate. So quad NAND gate, quad 2-input NAND gate, you know, right? So it comprises of these ones. So that is called the 7400 is the first integrated circuit, you can say. Okay. So then 1960s is that one, and again you can see the gap of 10 years to come to this speed, okay, to come to emergence of microprocessor. 8085, before that 8085, 8086, all those things. It took around 10 years for the development, okay, development or the innovation work of beginning of microprocessor, with Intel releasing the first commercially available microprocessor 404004 in 1971. In 1971, I was just 1.5 years old. We are not aware of what electronics is. We are not aware of what ICs are there. Okay. So in 1971, this is the development of Intel. They came into the industry and they started coming with, because their bread and butter and their product mainly on the processor, right? So those things they have come up with the microprocessor. First available microprocessor with very minimum functionality at the ALU, okay, arithmetic logic unit, or some comparators came up in 1970s. So that I was 1 year old. So that the technology got evolved, okay. At that time you are not knowing that electronics is the branch is there or not, okay, or not aware that semiconductor is there or not. But beyond that one, okay, so between 1900 to 1970, these are the things which are introduced. Because why I am emphasizing these things are, because the newer or the younger generation, okay, will forget all these things. They tell that it come as is, okay. So if we found out mobile integrated chips or some networking chips, or we are moving to 6G or 5G, right? If we are going to 6G, so it all developed in a, and somebody was who has done those innovation. It is for financial purpose has done. But if you see the contribution of all these technical leaders, so we need to really appreciate how the technology, how the semiconductor industry is growing, okay, and keep on growing like this. And then, so in this industry, right, 1980s, you are already aware, sir is there and all, I can give their own, how was our new generation when we are youngster, okay, when I was learning and when I was doing my graduation in 1987 to 91, okay, there was no Xerox also, we used to call it a cyclostyle. You must be knowing that, okay, cyclostyle machine. So on the electronics, and so that's why we have to come to this speed, because no gadgets, modern gadgets were there at that time, okay, no entertainment. So we used to go attend from college, you directly go to our home, so start working on it, okay, and whatever the hard work you have done because of this one only. Nowadays, whatever student, right, so even my son is also an engineer, right, so he used to see all PDFs, okay, that comes in the WhatsApp, and they prepare for examination with that one. It was not there in our times. You used to sit, we used to have a chair, table, everything. We used to write the equation, integrated electronics by Milman Alkias. So understanding electronics, integrated electronics by Milman Alkias was very much shared. So it is very, very toughest. Okay. So those things I am telling. And so from here, I can give you examples. Okay. Advancement of semiconductor fabrication technology leading to smaller, faster, and more efficient chips. So from here, my journey started from VLSI. So from 2000, I can give you all the examples, okay, which are captured in the next slide, okay, how the industry rapidly grown from 2000 and whatever we are there now, okay, the tremendous growth that in India we are moving to 6G, okay, in next quarter or in the end of this year. So earlier we were there in 2G, and now just a span of 6 or 7 years, we are catching up to 6G with wonderful activities and the wonderful networking speed we have it, right? So in 2000, application into mobile devices, consumer electronics, and automotive industries. So though I entered into industry in VLSI, that time there was no mobile communication. For your sake, I am telling you, I was not carrying any mobile phones, right? Cell phones were not there. I bought my first mobile, that is Nokia, okay, that is called Tube Light, something like that, right? So I carried that one in the year 2003. Okay, that time I paid 7,500 rupees. Okay, so that is the year which the mobile communication started. So even though I entered into VLSI, that time we are doing the IC fabrication or the IC design, which is power controller, okay, and very power regulator jobs, okay, or power regulator applications only. And then in 2000, the semiconductor application moved into mobile devices, consumer. Next. Okay, that is television and all we can say, and automotive industries. So in 2010, because of this guy, artificial intelligence, you can see here, this artificial intelligence and machine learning is taking our jobs, because whatever you are doing, the repetitive work, okay, the repetitive work or the regressions if you want to run, right? The regression and the repetitive task you are doing in the testing and all, it is taken care by AM and ML. Okay, so if you give the chat GPT or the co-pilot, so it will give the nice program to give you all the things. So that is also eating our things. So though we have invented this one, it is very good required, but these are the things. So from 2010, we are seeing a lot of tremendous growth in semiconductor design and semiconductor services companies. So where are we now? In 2020s, continued innovation in semiconductor material and processes. So as I mentioned you, lot of scope is there for physics engineers, semiconductor physics, okay, in understanding the material, so the properties. So you're not able to understand silicon, how the gallium arsenide, PbO2 works, okay. So there are a lot of scope, because whatever we are designing nowadays, okay, needs to have very good conductivity, okay, the various positions, and we are devising the transistor, okay, the gate, whatever the gate length I am telling you, right, that is a 2 nanometer. It relates to the gate length between your okay, source and drain. Okay, those gate length you are concising. Okay, you are shrinking it to 2 nanometer or 18 angstroms. Okay, so those are the things. What are the physical implications when we reduce the gate length? All those things are used here. So the current trends is like quantum computing and neuromorphic chips and all this. Okay, so this I will just give you from my experience. Okay, if you feel some any points here, if you want to raise, okay, with your application, with your devices. So from because my life, I told you, right, I born in the year 1969. From there, I will give how is my journey, okay, of using this semiconductor industry. Okay, even now also I am very difficult to use some of the advanced gadgets because of our tradition, because of our the born here, right? So we will be touching with electronics, because when we are switching on the VCR, video cassette and player, use because it was having lot of buttons. Okay, a lot of buttons are in the gadget, right? So we used to have. So this is the technology evolution is. So 1970s we had vacuum tube version. Do you remember anybody? Shivakumar Swami, okay. The company name I can say, because in my grandparents' home, so we had called Telerad, okay, brand radio, okay, which used to be having all the shelf and all for that one, okay, and the nice covers also for that. So it is because it is working with the vacuum tube. The dimension of this you can just, I am not exaggerating those things, but you need to appreciate where we are going. Okay, some of the youngsters, okay, lot of youngsters are there in this one, so they forget all these things. Okay, so electronics is just it started like this. No, so these are, that's why I want to quote all these things whenever I go to some technical symposium or conferences. When we are there, 1970s, this one. So Telerad brand, measuring 2 feet width, okay, and 1 feet the depth of this one, okay, and height is 1 feet. Okay, so this is the dimension, and the invention of tape recorder. Okay, so the compact tape recorder came in the 1980s. So we used to have, and again that time the crickets and all were used to be telecasted on the radio, right? So we used to have pocket transistors. So these are the companies: National, Panasonic, miniatured as compared to radio. So then came 1984. We have seen the television. I am telling you for all the youngsters. Okay, 1986. Okay, when Indira Gandhi died. Okay, and that year. Okay, so we had opportunity to see our television. That until that time we were not at all aware. I used to come to Bangalore. I am from Davangere. Used to come to Bangalore and go to MG Road to see on the show, in the showcase. Okay, so that was the story. Okay, how these things are coming. So that also vacuum tube version. Now whatever we have LED, okay, smart LED, QLED, and all those things are there, right? Organic this one. So these things, it looks very awkward, but I want to emphasize more on this one because we need to appreciate, okay, the experience or the journey of our semiconductor growth, semiconductor journey. So it is not a very simple task, okay. It started from 19, okay, one decade. So 1 century it is gone, and we 1.5 century. So these developments are come to this speed, okay. And in 1985, we have video cassette player, as you can see. So video cassette player and VCR, video cassette recorder, used to have, it was a very bulky one, okay. It used to weigh around 15 kg, around 7 to 15 kgs of weightage was there for VCR, okay. The same, whatever we have, MP3 player or whatever we have, right? So those things we cannot compare with that one. So then some of the companies, Akai, Sony, JVC, these are the companies. From 2000, what I want to emphasize on, just in 2 decades, okay, in 2.5 decades, the growth, where we are in 1985 and where we are in 2000, just you assume, okay, or just you imagine how the growth, just in 15 years, what all happened because of the semiconductor industry, the innovations, okay, the materials, okay, and the fabrication process and globalization, the demand, engineering capabilities, innovation engineers, all those things had led to these things. Because the demand was there, so similarly the innovative ideas came from the founders, innovative ideas came from the engineers, companies, okay, and the companies and the US support, okay, to fund for those things are started. So I like to introduce the word called nanoization, okay, nanometerization, right? We call it as from 2000, VLSI or nanoization came as a boom to semiconductor industry, tremendous growth in semiconductor industry from there on. So 2000, if you go on saying, okay, what are the devices we have? And coming to my bread and butter now. So I will go to, I will given the evolution, okay, over the industry. Then now we coming to market to survive because they are all private companies, they are not government, okay. So they want to find out the where they will do the survey, okay, where the market is there, which device the publics, okay, which device the industry needs, which device the market needs. Based on that, they will pour lot of money into it, okay, and based on that, they will carry out all this. So before I join into industry VLSI, the technology was called 350 nanometers or 0.35 microns, 1998. So this is the technology. So where we are, so 2000, we are there, 2024, 2023, 24, these things are already there in the market. Okay, the fabrication is there in the market. So you see, tremendous growth and tremendous progress in these technology nodes. So miniaturization, so that means we can, whatever the demand of the industry can be miniaturized, can be compressed. It is not necessary to have a board level design. Everything can be captured, okay, in a small silicon, okay, small silicon, we can call it package, okay. So that is of dimension, say 3 centimeter by 3 centimeter, we can cover the entire thing, okay, which contain billions of transistors, billions. Okay, so such a tremendous scope. So 10 to the power of 9 transistors can be accommodated, can be captured with the latest node, 2 nanometer. So just imagine, with only one transistor, whatever you can do, the inversion, you can do amplification, okay. But if you comprise these billions of transistors, just you imagine what is the functionality it will give. So then the physical implication, when you are comprising, okay, when you are compacting everything, billions of transistors in a single chip with measuring with 2 centimeter by centimeter, you see the impact of power, impact of the heat dissipation, okay, lot of things, it generates lot of heat, right? So we need to provide the thermal sinks and all. So those things I want to emphasize. So 2000 to 2004, we are there with the 0.18 or the 18 nanometer, 180 nanometer, 2004, 90 nanometer, okay, 45 nanometer. So, and 2004, 28 nanometer. So, if you have not understood anything, just please raise your hand. I will just try to, okay, make sure that whatever I am saying, so we should go positive. Otherwise, banda hoda anta agbardu. Okay. So 2008 onwards, we have moved to FinFET process. You know, right? So the main difference why you are going to FET, field effect transistors, and the NPN transistors, right? The field effect transistors, voltage control device versus the current control device. So you also know, right? You are all professors. You also know what are the main advantages of CMOS. Why we move to CMOS? Okay. So CMOS, the integration, the power. Okay. The integration means you can concise or you can keep everything in compact manner, right? So those things are the important things which is making the CMOS movement. So, and then in 2008, because of lot of issues we have found in CMOS, we moved to called FinFET, okay, FinFET technology, because it offers lot of opportunities or a lot of advantages, like minimum delay. That means if NAND gate, I will tell you an example, because I am proudly say that I am part of all this journey, okay. I devised, I did physical design for 0.35, so 0.35 microns, right? That is 350 nanometer, the standard cell light, you know, right? Standard cells in your design, okay? Standard cells are not the building blocks. They are called the bricks of any of your design. The standard cell height of your design during the 0.35 microns or 350 nanometer was 6 microns, the height of the standard cell. Now, if you come to 2 nanometer, your standard cell height, okay, is 0.158. 0.158. So, we can accommodate how many? 60. The height of it, okay? So that is called the electronics, that is called the semiconductor growth. So we can just imagine, so whatever the area which was consumed by this during this era to this era can be totally eliminated or came down to drastically, right? So that's why the intent of moving to this technology. And so these are the important terminologies I want to quote here. But can you say that these things are absolute? No. There are foundries still there. There are devices which are still there, which are fabricating from 350 nanometer. Can you tell where? In the higher the power electronics, because there they need the highest voltage level, the power dissipation, and all those things, right? Still there are industries that the higher power requirement and higher voltage dissipation, right? Still there are foundries which are working on this one, but the demand is very less. But the power electronics need all these things, right? So we need those applications. So currently we are in 2, and in Intel they call it as 1.8 nanometer, and that is called gate all around. So whatever you mentioned here, so these are the technology things, just to have a note of it, and you search in your Google if you are interested in VLSI, what is gate all around? So because the controllability is there. Earlier we are there, right? So in field effect transistor, so the losses were not there, okay? And the physical properties are in such a way that the loss was there and the power dissipation was going waste. We are not using the power which is consumed to this, and 10% of this power we have provided will be lost. So those things are controlled with gate all around. So we'll have a particular concise control of the induction of electrons, okay, movement of electrons through gate all around. So that is called FinFET. So the main reason we are moving to all these things is this one. The catch-up point is higher density integration. So a lot of chips, a lot of transistors, we can concise it, okay, we can fabricate it to perform the designs. How big you can dream, what designs you need, we have the solution. What that is the Qualcomm says, that is AMD says, that is Intel says. Okay, whatever may be the functionality of it, give the spec, we will give you the solution in a single package. Okay, so that is called that's why these things are very much required. So without the demand of public, without the demand of the market, they would have not come to this speed. Okay, and one more law I used to tell, I captured anyway, I captured in the next slides. So any doubt? So next, semiconductor industry overview. So where we are and what exactly is the requirement now, okay, and what is the strength, okay, why you want to come to semiconductor VLSI profession, okay, and where the tremendous market is there, tremendous strength is there in this, okay, tremendous scope is there, okay, and many things which are going on are happening now is this. So the semiconductor is very, very critical component. Wherever you see, okay, we need sensor, you need in the health sector, okay. So you come to agriculture domain, you come to anything, okay, you need wherever you need if you imagine that there the electronic comes in, okay, the semiconductor comes in. So in whichever area you want to dive in, so weather forecasting, okay, satellite, okay, and you come to any of the automation, automotive, okay, robotics, instrumentation, okay, and again mobile communication, networking, right, routers and the connected home division applications, all these things wherever you tell, so there the semiconductor, the electronics needs to be there. Without that, it is very, very difficult. So with software, we cannot control everything. So right. So because we need to have a sensor, that sensor can be controlled with software. The entire functionality will be done by your hardware. Okay, will be done by your semiconductor chip. Only 10% of it needs to be controlled. Where exactly the sensor has to go up or down. Okay, those things we are capturing it. Right. So for this one, you see, the semiconductor market would reach 726 billion by 2027. So this is worldwide request or worldwide the budget, okay, or the requirement of this. Why you are pouring lot of money on this? So these are the important segments where the money is poured or where the money is invested, right? So that is wafer fabrication. So now wafer fabrication, if it comes, okay, starting a new technology, right? I said you right, 2 nanometer. Nobody can start, okay, 2 nanometer fab, right? Because they have to invest billions of dollars. So only one company, okay, that is the foundry, TSMC, Taiwan Semiconductor Manufacturing Company, they are holding around 60% of the market, 60% of the wafers, okay, 60% of the industry, 60% of the global consumption of the chips are manufactured by Taiwan Semiconductor Manufacturing Company. They provide, even now also, they provide the chain, okay, they provide the fabrication from whatever the journey has said, okay, 0.35 microns to 2 nanometer, they are there, okay, industry standard. So rather than going to some other foundry, if we give some incremental amount, right, incremental fund to it, so we will be having that foundry. So they are the number one. So if we compare to the fabrication, okay, the TSMC, Taiwan Semiconductor Manufacturing Company is the one. So who supports all the evolution, okay, all the foundries, whatever I mentioned, the technology they have provided, okay. So that's why the important money out of this one, right, around 40% of the money which goes into this one only, fabrication, investment, okay, on the units, okay, investment on the units or the machines which needs to be worked on this. Other thing is assembly and testing. So once the wafer comes out, okay, and you one from the wafer, right, you take the die, okay, die out of it, you create the package, and then needs to be assembly and testing. So we need to do the testing that the unit chip will be testing, and then it will be deployed into the board, okay, for that one, and design and development. So these are the important segments, okay, wherein we are pouring all this money into it, okay, and major players, leading companies are already aware. Intel, TSMC, Samsung, Qualcomm, and AMD. Okay, they are pioneers in their own okay fields of the own domains. And other companies are also there. I captured only few things. Okay, and current trends. I told you AI and machine learning driving demand for more powerful and efficient semiconductors. So after AI has emerged into our software in semiconductor industry, around 20% of our jobs are at stake. Okay. Needs to remember all youngsters who are there. I'm seeing youngsters, okay. So that's why even in some day, right? So even the teaching also, right? So everything the chat GPT can explain. Just to come to the classroom and say, I want to learn basic electronics. Okay, open the Allen motor shed. Still there, Allen motor shed. Huh? Okay, Allen motor shed, and I want to learn some oscillator. Okay, Colpitt's oscillator still there, no sir? Colpitt's, okay. So Colpitt's oscillator. So it will write everything and okay simulation, and it will do what is the sinusoidal waveform, what is this one, okay. So the AI has come to that level, okay. But it cannot replace everything. But human resources are required still. But what youngsters with very high technical skills, which we need to beat the AI machine, okay, AI algorithms, then only will exist in the company. Otherwise, in the market, otherwise very difficult. That's what Just I'm done. I'm not exaggerating it. Okay, these are all the things which are there in the market. We need to understand that, and we need to further move towards that one. Okay, to come out, get a, and you jump the hurdle and come to that speed. So that's what I'm requesting. So growth of IoT devices, when we are there, right? So IoT was not at all existing. Okay, so Internet of Things, so you can go anywhere. So you can now only have all the your refrigerator, your door is open, that is there, that and all. Okay, you can open, you can start your cooking and all from your office only. Okay, and I have seen one of my cousin was brought on Tesla car, okay, and he came to India and he was showing in his mobile, okay, Tesla app, so he can switch on in his garage only, he can switch on his all the heater, AC, the garage and all the gates and all. So such a tremendous things are there connected to IoTs. Do you imagine these things were not at all when we are in 1985, when I started my engineering days in 87. If you are imagine anything like this, I am not at all aware of these facts. So agree or not? So these are the things how drastically, because why I want to promote my semiconductor thing is without these guys, okay, these are hardships, we are not there in this place. So it will be very difficult. So, and again the tremendous scope, we are talking about 6G technology, just I want to remove this 5G, okay, and we are moving towards 6G. A lot of work is going on in this. And future outlook, though we are there in all the segments, of the industry, in all the segments of the human needs, all the segments of science and technology, okay, all the segment of social and welfare, okay, but still lot of things to go ahead for youngsters, okay, a lot of things we need to work, okay. It doesn't mean that I am taking retirement, but we are giving more responsibilities to you so that we can carry forward our whatever the prejudice you have, okay, that we need to carry forward it. Okay, this is not the end of that science or the end of the semiconductor. Continued growth driven by emerging technologies, quantum computing. So we need servers which are needs to be operated at very higher speed, and renewable. So this is the need of the day, right? So we are moving towards the renewable energy solutions. So it looks interesting, these slides? Yes or no? Yeah, okay, good. So it gives more confidence on me that, so whatever you have heard, that it makes some sense to you. Okay, so it is not like just marketing slides, right? So now we need to understand where exactly we are going in, what are the segments, okay, what are the segments semiconductor industry wants, okay, and working on it. So whatever I said, the companies, Qualcomm, Cisco, okay, AMD, they're not coming to every domain, every field they won't be coming. Philips, Siemens, they are into their biotechnical, okay, biomedical kind of things. Okay, they slowly introduced to some other field, so they came to some other domain, but they spent a lot of money, but came back again because they want to go in this one only. Automotive. So in automotive industry, Infineon. So Infineon, they are pioneers in providing the infotainment. Automotive industry, okay, the requirement, ADS, okay, ADAS and all, right? All those things are given by the company. Those are the initial segments that covered. So to support that one, so this slide which explains what are the semiconductor industry segments we have. Computing and data storage, you are already aware of it. So talking about AMD, GPUs, CPUs and all which are operating at the speeds which are tremendous speed is there. Wireless communication, in these components we are designing the RF chips, modulator, demodulators with higher speed, and then automotive. So these are now in India, we are slowly moving to ADAS only. All Mahindra and all, they have come up with so much of utilities or so much of features, but still it is under control, even it is under testing mode. But in US also, the people are hesitating to use for ADAS. But even one of my cousin told that even they can book with automated, okay, that means you can book from Uber app, right? So similarly, driverless car will come and pick you up. So those are the things which are happening now. Okay, and it will in 1 or 2 years it will come to our market also. There is no surprise. So a lot of scope. So why I want to say here is in all this field, lot of scope is there. That's why automotive, billions, or suppose 200 or 250 billions of the money has been spent on this automotive electronics, whatever I said, in Infineon, okay, and NXP, okay, the Qualcomm, okay, those are companies which are pioneers in providing the automotive chipsets. And industrial electronics, as I mentioned, right? So industrial electronics, if you have a power controller, where voltage regulators, okay, where you want to devise, determine or design any inverter circuits, there we need the industrial electronics. Though the investment on these things are not, but these are things are required. And consumer electronics. So whatever we are there, that is there on the consumer electronics. And wired communication. So whatever networking chips, routers. So these are the 6 key segments in which semiconductor industries are working. So first, computing and data storage, Micron, SanDisk and all for data storage, and computing your Intel, AMD, okay, Qualcomm, for that one, all PhDs. You see their faces, right? They would have slept around 15 days back, right? So they will be they will be always there in the lab. So I have seen so many guys who are there in Intel, Qualcomm and all I worked. The scientists are used to be like that. They are all called as distinguished engineers. They can directly talk to CEO. Qualcomm CEO can talk. So he is a distinguished engineer, distinguished fellow, right? So next position of whatever vice president, right, to company level. So they're working their bread and butter. They're from beginning of their career, right? They started with that one. Lot of R&D activities they do. Okay, lot of results they produce. They will give you in-depth analysis of any chip failure. The main problem, what I have emphasized here, is only if the chip works. If the chip doesn't work, okay, then all our jobs will be gone. They will lay off the entire team. So even I was also the culprit in one of the company where I was working in a company called Mega Chips Corporation. Okay, it's a Japanese company. The Japanese, the culture is that they give more emphasis onto the quality. So you can postpone your release of your chiplet, okay, chipsets. But the quality, whatever the 100% quality they have to assure. If 99.9 they reject. Okay, but in one of our product, okay, failed miserably in the test. It was not so it was not already shipped to our customer. It was in the market in our laboratory only. So about 600 people of that team laid off. Okay, in the next 2 days only they called everyone to this one. They didn't say all these problems and all because everyone has to take the ownership of that one. But so 600 members. So the quality. So because in private company, it is not, they are not running any charity. They say clearly, okay, everyone can be replaceable, even in CEO also. Everyone, so even CEO when he addresses any of the chip failures or the chip success, it tells that one only to get the confidence to say that I am also there with you, right? Like whatever our beloved PM is there, right? So whenever he goes, whenever we have failure and the success will be there, right? So same thing, the company and the corporate culture is that one. So everyone is questionable. There is no hierarchy. You have your own responsibility. You need to deliver. CEO has his own responsibility. He has to deliver. So if your tape out, what we call it in fabrication process in the semiconductor design is a tape out. That is the last step where from here it goes to the fab, whatever TSMC, right? If the deliverable is there today evening, Friday, okay, so then everyone has to be there in your, we call it as a war room, like this I'll be having. So war room is like all the department heads will be there with engineers, okay. We used to call our physical design engineers as linemen because we are doing a lot of routing. You know, right, what is physical design routing will do, okay, taking from wire from here to a stretch and all those things. So all the department heads, so when the chip, the layout release is there, we have to work like that. So just I'm telling you, giving you the corporate structure of working, okay, and how the chip, everyone is questionable, everyone is accountable, and everyone will get the opportunity to work towards the growth. If the chip failure is there, you will get whatever you want, okay, you can enjoy, you can take 1 week leave and go. If the failure is there, next day you have to come, you have to be there in the office for 15 days, 15 days in Qualcomm, okay, 15 days in AMD, you have to be ready to debug the problem. Okay, so that is the core strength. Why I am saying this is the team effort. So this cannot be done single army, it is not a part of the single man army job. So everyone has to contribute. They have to accept those responsibilities. Mr. Vijay is responsible for physical design of a big block. Okay, he is responsible for it. He has to deliver it. Okay, design verification. Sir is doing verification job. He has to do it and deliver it. Okay, and sir is doing RTL design. He has to deliver it. Okay, standards and libraries. Sir is doing. He has to deliver it. Any problem comes, so that's why everybody has to be responsible for that. So these are the industry segments. So then I will hello sir. So then next I will introduce the new, you are already aware of it, I touched upon the TSMs, right? So semiconductor foundries or fab. So here, so what exactly, it is like our to mechanical foundries. Similarly, we have the called as foundries, semiconductor foundries, where the vapor would come out, okay, and it will be tested for this. So you are also known as fab, or specialized facilities where integrated circuits are manufactured, okay. And there are two types of foundries. One is pure play foundries. These foundries manufacture ICs for fabless companies. We have in semiconductor, we have fab and fabless companies. Okay, fabless. So accounting fab or developing fab, putting a lot of effort to on fab development is because billions of dollars needs to be invested. So that's why everyone will not go to that one. Okay, even Qualcomm, AMD, okay, NVIDIA and all, they are all fabless semiconductor companies. They take Mr. TSMC, okay, the service of TSMC, Global Foundries, okay, UMC, but Tower Jazz and SMIC. Okay, these are the foundries, like the foundry domains. So these are, that means I will give order for you. Can you fabricate and give me the chip? So it is like whatever the fabrication you do it, right? On the same aspects, so these things all work. But how much? What is the vapor cost? How much you have to spend? Okay, what is those things are the commercials, right? So then integrated device manufacturers. These are the companies design and manufacture their own ICs. So the R&D, everything their own ICs, okay, own R&D, own design, okay, own infrastructure, everything until the design GDS, okay, until the GDS or the OSS which goes from the physical design. Examples in say these, they are owning the companies design and manufacture their own ICs. Examples include Intel and Samsung. So these are the guys, okay, who does designs. They have their own fabs. They have invested a lot of money on it. And Samsung, Intel and Samsung are their own product line. They have their own foundry system they can use with the technologies, with the need of the requirement, the product requirement or the industry requirement. Based on that, they can produce. So these are the important foundry types. If you are not necessary to scratch your head on this, okay, these are the business things, okay. And major players in the foundry, TSMC, the largest pure play foundry, holding around 55% of the market share, 55 to 60%. Samsung Foundry, the second largest with approximately 18% market share, and Global Foundries, okay, another significant Global Foundries. So these are the fabrication steps. So what are the key process? We'll do it in foundry. So wafer fabrication, the process of creating semiconductor wafers, which involves multiple steps, including photolithography. Photolithography, etching, duping, you are already studied in your VLSI. Pucknell, right? Okay. So we have given all the list. So I wanted to emphasize on it, but because of the lack of time, right? So if you call me for some other with some students of VLSI domain, right? I will give you more phenomenal changes, okay? Okay, those things I can give you that. So packaging and testing, this is fabrication from foundry, and next comes to packaging, okay? So you are from the wafer, you take out your die, okay, you do all the packaging, and then it goes to the lab. It is done. Is it for the we give all the stimulus, okay, the stimuli for that one, and record with your all. It is like your lab facility only, lab. Okay, the CROs and the cathode, the oscilloscopes, everything they will be having all those setup. So whether we are having the same, whatever the requirement, what is the spec, and what is the, we are meeting that spec or not, we are measuring that. So then, where exactly the market trends are there? Increase the demand, growth of AI, IoT and 5G technologies, supply chain challenges, and future outlook is advancement. Process node, you say 2 nanometer, and new materials you said, right? Semiconductor physics, capacity expansion. So next, if time is there, just I have sufficient time, right? So 15 minutes time. Okay. Sir came, no, that's why I thought. Okay. Okay. So just these things which comes to the my main work. Okay. Trends and challenges. So whatever given, so you can just browse on the if you get all those details. Okay. You will get it on the Google. Okay. And you get it on the internet. Okay. So but here, so what are the trends? Okay. And the challenges which I will emphasize more on the physical design aspect because I am physical design expert, I can say. Okay, because I'm working in 24 years in physical design, I want to give that one. So though I worked in all the domains, but my limitation is limited to only physical design because it is like anyway, for any professor is there, he is doing antennas. If any professor is there with the analog devices, then he will be called as master or professor. Okay, in that analog devices, he knows in and out or when the voltage control device or the current control device with all parameters R and L and C can be varied to create the environment, right? So I will cover my main thing here. So what is the expectation? So everyone expects, I want to move to iPhone, whatever the family develop, i16, I really don't, I have not used it, I never used the iPhones, but say 16, 17, why they are inventing, why they are coming up with these things? Because based on your customer requirement, the design requirement and the trend, how the industry wants to go, you need to catch up. If you are not catching up that one, why Nokia vanished in the mobile market? Because they hesitated to move to the smart phone section. Before that one, Nokia was the number one. Even Samsung was not there at that time. Yes or no? 2002, 2004. They are hesitant. Yeah, no, a lot of tremendous scope is there. The analog kind of thing, or the with these capabilities, keypads kind of thing. So they have not moved. So then Samsung got into market. Okay. So these are the things why you want to be in semiconductor. All companies, as I heard, so if you go and talk to anyone, they are doing business. They are not into charity show. Okay, they want to make market. They want to come to the speed. What NVIDIA CEO says that. Okay, they want to bring. Okay, their devices first. Okay, which is super fast. They say super fast, and they have to come to the market. And suppose say they wanted to 2026, they want to launch some semiconductor chip for the entire package. So they will be there in that market. Otherwise, 2027, if you slip it, your market will gone. So all the investment is gone. Okay, so that's why you are there. So market or consumer or my expectation is that compact your phone or whatever the gadget you have. So I told you that time when I started using okay my phone, okay mobile phone, I purchased with Nokia 2100 by paying 7,300 rupees in way back in the year, sir, 2003. From very limited store that still I remember the shop. Wherever I used to go, I used to introduce even to my family members also. This is the first time I purchased my mobile. And I did because we are older guys, because we are all, so you are not like younger generation which you understands everything because it is new to me. Mobile industry was new to me. I read the user manual 3 times. Right, 3 times because it is new gadget for me. So sir can tell, anybody can tell, right? So because I am not telling you that I am not so smart, but we want to be qualitative engineer because I am in the engineering, right? So what each button used to do, right? Or not aware of it. Okay, don't take it as this thing. So because the user manual I read 3 times, okay, and I got super enjoyment because it is my first gadget, no? Smartphone, not smartphone, there is a very basic phone, 2100 Nokia, 7,300 rupees. Okay, so I got enjoyment. So I have not slept, I am telling you frankly, without hesitation. So because I want to give that whatever the tremendous, because if we get whatever the new devices nowadays, right? This is, if you give it to any child, you know, who is in the 4th standard or 5th standard, they will operate everything. Even in my phone, I have not used so many features. If I tell to some other guys who are in technology standard, but why do you need those, right? Features. I don't need it. That's why I have not explored those things. Those are the things. So what you need now? Compact. Okay, everything needs to be available in this one. Okay, less power. So it should be, your device or the gadget should survive for a week. Is it possible? How do you want? So these are the expectation, the industry, the requirement. Even I myself also tell these are the requirement. Need to support all the available function. It needs to be supporting all the available function, PPA requirement. So this is what the first point, power performance area. So whenever, when you are in VLSI industry or in any of the design in your semiconductor domain, these are the mantras: power, performance, and area requirement. So you need to give a high efficient system where you will get a very good trade-off with this power, performance, and area requirement. So performance must be very speedy, area must be concise, and power should be very less. The company which brings the new product in the market, okay, time to market must be rapid. So it should be. So that means whoever is inventing new devices, it needs to come to the market to attract the or to capture, okay, the pulse of engineers or the consumers, okay, then you will win the market. If he slips that one, so his market, whatever the budget, okay, whatever the investment is poured, so it is gone. So the time to market is the key point. Core competency, because you are seeing lot of companies are coming in, okay, with major devices, okay, major requirements. So that's why we need to catch up. What is required for you? Is it we have to do the technology survey? How is the pulse of the consumers? Whether when I launch the product, how they will take this, how they will absorb this, whether I will get some margin, whatever the investment I spent, it will come or not. So those things you have to do. So key challenges. Now I told you, right, why I have to come from 0.35 microns, okay, 350 nanometer to 2 nanometer, right? So these are the key. I told you, right, so I used to design a standard cell, okay, I used to design an integrated circuit or the semiconductor or the ASIC chip, okay, in which the standard cell height was 6 microns. Now in 6 microns area, we can accommodate around thousands of transistors, thousands of standard cells, okay. So the requirement now, or the designer or the market need is that how big you can dream. I dream such a big billions of transistor. I want to use that chip. So if you have that requirement, yes, we have Intel, AMD, Qualcomm. They say that we have a solution for it. Whatever the function you give it, we have that capability. Okay, with the confidence on the team, technical team, we will provide you the design with all the things, okay, meeting your specification. So that's why, so design complexity increase. Few millions of transistors, we moved from millions of transistor to billions of transistor. If you see, if you enlarge it, okay, if you do that one, right, survey of it, okay, we'll have. So here I am introducing Moore's law, right? So is the Pitama, so is the Intel founder and all. So the Moore's law states that in semiconductor design, okay, so your design transistor size, okay, doubles for every 18 months. 18 months. So, but now we are captured, we have overtaken that also. Earlier was that one about a decade back, no sir. So this Moore's law was good. Now we have overtaken that Moore's law also. So you got it right. Your complexity, design the complexity doubles, okay, increases by 2 times, okay, in just 18 months of time. So we need to catch up that. But currently we are not with this one. We have even bypassed. We have crossed Moore's law expectation also. So that is the requirement. That is the industry requirement. Industry requirement. Why I am emphasizing this is youngsters has to know these are the industry requirement, and you need to come to the speed. You need to get to the speed without understanding the basics. I am telling you, you have to give emphasis to 0.35 microns because all basics or fundamentals in semiconductor must be strong when you are designing 2 nanometer designs, right? So those things. So then low power. This is the key requirement now, right? So your mobile, okay, or whatever the application you have, it is operating, right? So handy or the compact, okay, sleek, okay, we need to have that one, and which is needs to be repowered, okay, it needs to have low power, it needs to be operated in the low power, okay. So in this low power, lot of tremendous growth is there, okay. So P is the power is equal to I into R or V into I. Okay, sorry, V into I. So these aspects, when I am designing any ASIC, when I am designing any semiconductor, so everything I have to go to this one only. We call it as voltage drop analysis. What is the total power consumption of your chip? So your chip contains, the integrated circuit contains lot of parameters, okay, power domains, everything, okay, all those things. So for the another 5 minutes are there, just I'll try to cover most of the things, right? 11:50 now, sir. Okay. So okay. So low power, understood. So this is the major requirement, power performance area, okay, and now you are called as yield, okay, because coming out of the fab, how many chips, okay, how many wafers, and then how many dies are productive, okay, we measure that as the yield, okay, what is your yield, okay, what is the manufacturing yield, whether everything can be or fabricated or coming to use or not, it needs to be wasted. In 2 nanometer, they are spending billions of dollars, okay, millions of dollars for one mask, okay, we call it as the base layers, metal layers and all. I will tell you in this one. If anybody interested, please contact me. I will be wondering, so I will be roaming around, right? So we'll discuss on that. Okay, so solutions for handling. So whatever the problems I have told you, I will give you the solutions also. Okay, because we are all engineers, we must provide solutions. If you say some problems and get lost from here, no. I have the solution, how we will conquer all these things. Whatever may be the design complexity, I have the solution in my physical design aspects or in any of the design part side. Okay, we are there. Oh, we will divide the entire design, okay, SOC or billions of transistor, hundreds, millions of standard cells, instances we call it as building blocks. When you are building a bigger, okay, or very vanish kind of house, this one, right? So you're coming up with, how do you do the floor plan and all? You must have spent a lot of money on that one. You have spent a lot of things on the concrete blocks and all. Similarly, we'll divide the design into different partitions, different blocks, modules, and then you will integrate, divide and conquer it. Okay, divide the design, okay, and conquer it separately. Okay, do it integration and bring it at the top level. So blocks are run in other sites. So what are the advantages in this? But fast turnaround time with accurate models, fix this one. And I will also want to touch upon this. It looks very interesting, right? You are not heard of this one. We have 3D IC designs nowadays. Lot of some very few companies are spending lot of money on 3D IC design. Sir may be knowing everything. So Intel, okay, AMD, Qualcomm, okay, and NVIDIA, they are already there in this 3D ICs. So that means, so far I have started from my semiconductor. Okay, what is semiconductor? Right? I was talking in my first slide. I coming to here 3D IC designs. So what we are doing here is heterogeneous. Heterogeneous means so far I have touched upon only homogeneous, right? So that means so everything on the same wafer, same technology, same node, same foundry, or same technology node, same fabrication node, okay, same design rule sets, 28 nanometer, entire SOC, but we are doing called as chiplet designs. Okay, this is the chiplet architecture where we can stack together, okay, stack together different dies. One is at 40 nanometer, one is at 28 nanometer, the other chip, this one stack, right? So it is 2 nanometer. So these things are integrated. You see the technology, we see the innovation, okay, we see where exactly how powerful are these semiconductor industries. We have a demand for billions of transistors, we have this one, and we have these guys, okay, but I am telling you frankly, I have not worked on this. So the things are going on now. We call it as 2.5D, okay, and 3D ICs, lot of chips have come out, okay, 3D ICs, NVIDIA, they released that one, and it is going on with 28 nanometer to 2 nanometer, we can have it with a single package. The different packages, the different board level can be removed. Whatever the design complexity, we have the solution with stacking together the chips, stacking together the wafers, okay, stacking together dies, okay, and providing the entire package. That is called 3D ICs. Yeah, so because the design complexity, I told you, right? The design complexity, and I also told you that some of the applications, power applications, cannot be possible. The regulators and all not possible with 2 nanometer. It needs to be there in 40 nanometer only because of the power requirement, because of the heat dissipation, because of the thermal runaway effects. It needs to be there. So that's why the first stack will be 40 nanometer power regulator applications, and some of the analog ICs are there, analog IPs are there, right? Though because the analog and the digital, you know the differences, right? Analog will be very susceptible to the noise, needs to be handled carefully. If we introduce to 2 nanometer, it will not survive, it will not operate. So that's why it needs to be therein, because to overcome the physical design effects, when you do the fabrication, no sir, you do all the base metal layers, then metal one, everything will come, right? So during the fabrication, they will not withstand the tremendous pressure or the tension on those things. The things will break down. Because of that one, these are the specialities of those applications in their own application domains. So if you have a chip, if you want to incorporate all those things, right, it is called a system in package. The entire system is there in your package. So then this is the solution. You got it now, sir? Okay. So then scalability. So because I told you that billions of transistors you can accommodate, is it possible to run? Because ultimately you need to do all the implementation, all the simulation you have to run, okay, and all you have to run all the physical design activities, and needs to be fabricated. Before doing the fabrication, it need to do timing analysis, need to do the dynamic simulation, okay, we need to do the physical DRC and always closure and all. It needs to be worked on a very big machines. They are operating at the distributed computing machines. The servers, you know, right, analog Amazon Web Services and all, they provide on the computing resources on the cloud. You take them for the rent and you execute that. Okay, it will be there in US or it will be there in India, it doesn't matter. Okay, they will give the money and they will give it. Okay, so these are the important things we are using. So those challenges are there and these are the solutions. And I told you, right, sir, I told you for chiplet, right, reusability. Suppose if you want to build a technology or if you want to have an IP is there, intellectual property, you know, right? Your company has developed a 28 nanometer. Suppose I am with the other company, I am coming up with the system level, okay? Then why you should spend more money on this one, right? I will use your existing company by paying royalty, by paying your money. Otherwise, I have to spend lot of money on the R&D and all, right. Your specialization is that sensor. Why I have to invest, right? So I will take you say that I am available only in 28 nanometer. I don't have time for you to wait to give it at 18 nanometer or 12 nanometer, right? So that's why I take this one. I will take this one, right? And then you do the heterogeneous designs. Yeah, complex, yes. I will tell you that, sir. Yeah, we call it as through silicon layers, right? You see the complexity, right? So because it has to come from the 28 nanometer to pass it on to your 18 nanometer, pass it on to 2 nanometer. So we to connect all these things, right? Interoperability is there, right? The multiple stacks together or the multiple dies are connected together during the fabrication called through silicon vias. Through, okay, all these things will be punched together, okay, and will be connected to this one. And for the verification environment, who are there in the design verification side, okay. So we use here, there is a one more express protocol is there for doing the 3D ICs. So the verification part, the design verification part can be done with that universal chip interconnect, okay. Universal chiplet interconnect express. That is the ultimate technology we have for the 3D ICs. So you are operating at all these technologies, all the design side, so that is the protocol, the current existing protocol to make you the 3D IC works. Okay, so those are the IPs. UCI is an IP which is developed by Synapsys. Synapsys, you know, sir, Synapsys, Cadence and all EDA. Okay, EDA founders, EDA Pitamas, right? They give those IPs, you need to integrate it. So when you are developing 3D ICs, these are all the overhead design. When you are quoting the budget, you need to consider all these things. You cannot quote like Karamandaki, you cannot down where you call it, right? Karamandaki, go and purchase. So we need to consider all those things. So technology and all these things are the keywords. And when you are doing the budgeting, and also you need to consider all these things, the IP level thing, the foundry requirement and all. This is the key picture. Whoever is interested to do a lot of R&D in this one, right, go and do it in this one, low power. Because whenever you go, wherever you go, right, so this is the demand of the day now. Okay, low power. So how best you can provide. So suppose I have talked to you about billions of transistors, millions of instances, millions of chips, okay, or the chiplets working on with multiple dice and all. So then, what are the methods which are available in this? These are all, it looks like very simple, but implementation, verification, so implementation you can do it, but how do you do it sign off? How do you do it like handshaking, okay? How do you do it? How do you do handoff from this one? It works fine. We have EDA tools. EDA tools are mature enough to do that, right? So those things are done here. Okay. So this is the implementation of low power designs. You must be knowing multiple power domains, power gating, DVFS. You have studied this one, right? DVFS and all you might have studied in your college days. Dynamic voltage and frequency scaling. Because so the power, right? Power is always, it is series quantity of, right? Your load capacitance. V, the quadratic effect, V square into F. F is frequency, performance. Okay, voltage, your power mode of that one, right? So dynamic voltage and frequency scaling, dynamically we are changing the voltage of your design. Dynamically, based on your requirement, how it loads, and which station it is operating, which domain it is operating. So dynamically we are changing the voltage and frequency. When you are changing dynamically, we can reduce the power, yes or no? CV square into F. So that is called, and this is dynamic and adaptive. So we'll have a closed loop control system where we take the signal, okay, output, which demands how much voltage, okay, it is fed back to the controller, which generates the voltage, which generates the frequency required for the design. It is, for saying it is very simple, but designing the controller, adaptive, right? So adaptive, we have a closed loop system, closed loop control system, where it sees the result and checks the stimulus. Okay, it applies the stimulus to your design. Voltage and frequencies are changed based on your time scale, picosecond variation, that is called AVFS. Design architecture changes, clock gating concepts, bring new technology. Yes, yes. That is the clock gating and all you can discuss. So again, coming to manufacturability. So far you have mentioned you about the architecture, about the design thing. So always, if the design is not manufacturable, if your piece of whatever the design you are doing is not manufacturable, it's useless, right? We are very good in doing all the designs theoretically, but if we cannot come to the market, okay, without manufacturing thing is useless. Okay, everything is interconnected, everything needs to be handed up carefully. Then what are the manufacturing challenges when it goes to foundry? They are invested a lot of money on it. So what they need, it must be designed for manufacturability compliant. They cannot fabricate your design which is not compliant with this. Design for manufacturability. So many checklists will be there. Checklist when they are from the automotive industry, right, when they are delivering their car, your car, right, from the showroom, they will fix all those things, right. Similarly, they will do 1 month of checking on your design, whatever we produce, right, GDS, okay, the geometric description stream you file it release, right. They will do 1 month and they will have lot of checklist. Everything should pass. Okay, then only they can. Otherwise, they will not take your design to fabricate it. So if everything goes fine, timing, your production, your manufacturability problems, DRC, LVS, whatever is said, right? So those things are there. So how to take care of all these? Don't worry, the life will be miserable without any automation. We have all the tools. All the tools are available. They are casting like anything. Okay, they are all. Even if you buy one synthesizer, okay, RTL2 logic gates, okay, synthesizer, that itself will cost you millions of dollars. If you say one package, if you say place and route tool, sign off timing analysis, prime time, okay, cadence tempers, right, all the DRC, LVS, caliber, IC validator from sign off. They are all very expensive tools. We have all the tools are available. Our life is simple now because we need to master in those things and try to resolve the problems. Ultimately, the question is again the big question mark I put is all devices are cheap work to move to non-planar device. We call it as a non-planar that is FinFET. Okay, R&D cost. How much is the effort? We see here. Okay, when you want to come out with a working chip, okay, and 2 nanometer, what is the cost it is involved in this? I told you so far. Okay, is it really worth by NVIDIA or AMD to spend that one? Yes, the requirement is there. That's why they produce all these things. So I come to this one. Okay. So far, thank you very much for peacefully listening. I don't know whether these things are very productive for you. Are you interested? But so I try to cover most of the things which is happening in semiconductor industry. Okay, how the growth, how was the evolution? Okay, how was the journey from 1900? Okay, to 150 years. Okay, how was the journey from starting to now? Where exactly was there? What were all the pitamas? Okay, founders who have worked hard to come to this speed, right? That I touched on. And light on key techniques, challenges, and I also propose some of the solutions. So now need for an hour is to take extra care before the new advance. All those things needs to assemble, digest these things, understand these things, and come up with the methodologies. So, sir, coming. Yes, sir. Now it is reserved for questions and answers. So whatever Rudraswamy sir says, I'll give this one. I'll come to you only. Don't. Huh? Mm-hmm. So semiconductor manufacturing company.
So what is the role of this
Chandigarh you are telling? Chandigarh unit or
no, not
CDAC, right? CDAC.
that is in Gujarat or TSMC Power Semiconductor.
Mm-hmm.
They have introduced for the requirement of chip requirement in high power requirement like car and some regulators. So TB tech and this TSMC.
Yeah, it all depends on the manufacturing process.
Requirement of this type of
the automotive, right? So in automotive requirement is there on the and even the solar. I told you right, renewable power energy. So all this I will tell you. So why you have to move to this the renewable power energy, right? The solar panels and all. So we have retractable and
maximum focus now industry in the low power, but for the chip design for the high power, that is also
yeah, that's what I this is in the power electronics sector.
Yes.
Okay, in power electronics sector, I told you the physical property of power electronics sector which doesn't need 2 nanometer, which requires on 350 nanometer 0.35 because the interoperability and the PPA and the power susceptibility, okay, the drop, everything which works fine for that one. Otherwise, we cannot have the thermal sink, okay, the dissipation for the heat which is absorbed, right? So because these guys, the PPA and all will be very much. Okay, so that means we need to provide thermal sinks. Otherwise, your chip will go into thermal runaway effect. That means it will not work on the reliability. It may work for 1 year. Okay, reliability. Suppose if you are if you are producing the IC which is going to space, okay, satellite, okay, and if it works only for 6 months, no life, right? So that's why we'll have it as a reliability effects, sustainability, reliability. How maximum? What is the probability that your chip will work? For those things you have to calculate. So whatever you said, it is not necessary.
Now the transistor available for the voltage of 32 volt and this 70
exactly.
volt.
Now what I am telling you, 2 nanometer is it is working. The transistor is working at 0.6 volts.
Yes, only. 0.6
volts, right? Whereas in 0.35 it was working at 3.5 volts. Right? So here you can see the threshold because we have the gap right between the logic 0 and logic 1. We are very lucky that we are working on the digital design, but not into analog. If you see 0.6 volts, that means 0 to 0.2 volts it is considered as logic 0. The gap of just 0.2 to 0.4 volts is your forbidden state. You cannot say which state it is there, right? So that's why that is all the physical effects are there. I will give you on the next this one. Okay, Rosen. Yes, sir.
What do you mean by
technology node, whether it is gate length or channel length.
The gate length, that is the channel length, right? The channel length which is formed between the source and drain. Okay, so those things is the technology node. So I will tell you, I will come to you once this zone is there. I will draw it and show you.
In general, gate length and channel length. Thanks for your presentation.
Yes, sir.
I have a question related to PD. For PD,
Come, sir. PD is the one guy. Good, good. So what do you know about PD? You tell me now.
sir, when it comes to PD, we know that input files are required like a dot read, tab file, dot SBC, and then these are the input files are required. Input file, there is a connectivity from synthesis team to PD. So then how the connectivity takes place from synthesis team to DVT, sorry, PD team, from PD to synthesis team, how the connectivity takes place.
Okay. So, sir, I have time na to answer this question. Yeah. Okay. So, yeah, it is a very good question. So, maybe others, just I will give one recap to everyone to understand this one. So, this question is very genuine to me, okay, and it is for physical design engineers only, right? So, this physical design stage is, I told you, right, it is like lineman and it is like mason worker. Okay, I will tell you, because you are building the blocks, we are responsible for doing it to work in the fab, okay, with all the deliverables, which is coming as all the layers. It is whatever is said, right? Millions of dollars for your masks. Each layer is coming as a mask. The production of the connectivity is there, right? So that is coming as mask. So what this question is that the synthesis, you know, right? So once the design is done, RTL is done. So register transfer level, all design is coming and they are coded into Verilog or VHDL. So they are all in the high level language it is. It cannot be understood by the tool to do the fabrication, because everything needs to become as a building block, standard cells, IPs, macros, right? So that's what these are all the libraries. So whatever the inputs is suggested. So earlier there was a big gap between synthesis and physical design. Now synthesis is also part of my work, physical design. Okay, because we call it as a physical aware synthesis. Because all the physical inputs you are giving, as you mentioned, left is the library in the exchange format for your standard cells, IPs and macros, and dot libs are the dot DBs. They are the timing libraries, crosstalk libraries. Dot V, that is the design contents, Verilog. SDC, synopsis design constraints, and one more file I told you, UDF. That is, it is coming as a part and parcel of your these design packages. We call it as a collaterals, input collaterals. We take those inputs. Okay, I told you, right, earlier there was a gap between synthesis and PD engineer. Now that gap is not there, it is in my domain only. Synthesis, when these inputs are given, it provides you the gate level netlist. So gate level netlist are physical designable. Netlist, yeah. Gate level netlist is generated. From there, the physical design you have to do the designing checks, sanity checks on your design. Okay, all the floating input, floating out, channel layout, all those things, timing relations, SDC are the constraints, all those things, right? Understood? Any questions?
One more question. When it comes to sign-off, right, there are 4 different sign-offs are there. So after routing, all the sign-offs should be
Yes. No. All the sign-off, I will tell you. Because how we can do fabrication, right? So power is also this one. Performance you have to do, manufacturability you have to do, right? So all this goes as in parallel, because there is no connection. Timing sign-off first, prime time run. First it has to go to your parasitic extraction. All your wires, okay, which comes to RLC, impedance RLC, right? So everything will be dumped into SPEF, standard parasitic exchange format, you know, right? DSPF, SPEF. SPEF is connected to, because you are calculating the interconnect resistance and capacitance, it is given to prime time. Prime time calculates the delay analysis, static timing analysis, delay computation. Then SDC is given constraints. What is the requirement, the design, whether meeting the timing or not. That is done by prime time. Physical DRCLUS, caliber, mental graphics tool, IC validator tool, that will say it is DFM, DFI compatible or not. Power, EIREM, IR drop and EM. Got it? All these things, when everything says smiley, then you can go. Otherwise, no. It is iterative. Got it? Okay. For the advent of this, okay, next speaker wants to talk. This has to. Okay. Yes, sir.
Sir, if you have fabricated one IC, designed one op-amp, let's say, then I send it to foundry. Now, what is the security that they will not copy my circuit and
Sir, it is a valid question. Okay. So, sir can give that one. These are all the trust, okay, the proprietary information, right? They will have, okay. So, we have the non-disclosure agreement will be there. So, even if I want to enter into some of the ODCs, okay, offshore design centers, right? I need to sign NDA. I cannot use, okay, my mobile. I cannot take, I should not take in this one. These are the mutual trust. If you are not following that, your company has to be penalized, and there are so many things which are ARM, right? Your Qualcomm is showing ARM or ARM, the vice versa is going on, right? They will be penalized. Okay, they have to, the legal criminalization, everything will be there. That's why it is all mutual trust. When they sign NDA, it is, when I am entering into JSS, this university, you have certain rules, you need to follow. If you are not there, you are out of the market, you are out of the business. Okay, that mutual cooperation has to be there, mutual trust. Yes, sir. Thank you. Thank you very much.
Thank you, sir, for your insightful
Thank you, sir.
lecture through. It is like a combination of professional academician and industry person. So he traveled us through basic semiconductor industry segments to the application level segments like AI, IoT, and 5G communication system. Thank you very much, sir. So now I request TRM sir, SPK sir, and coordinators to honor the speaker. All of you, please assemble near this hall for tea break, 10 minutes. Thank you.